Mhm.
Okay, cool. Yes, thank you very much, everyone, for showing up, and also thanks so much for the invitation to this seminar. I'm very, happy to be here, even at least virtually. So I'm Ryuji, and I am a postdoc at NTU Singapore, Nanyang Technological University, Singapore. Just please feel free to let me know if you happen to be in Singapore, so that we can just hang out. Yeah. But yes, so today I would like to take this opportunity to tell you a bit about our recent works trying to characterize the manipulation of general dynamical quantum resources. So this talk is basically based on these three references, but they share all the interest in the characterizing the manipulation of the general dynamical quantum resources. So the first one looks at the conditions for such a transformation to exist at the level of general resource theories, and we look at some channel manipulation. We introduce such a framework first and trying to characterize that in terms of the resource quantifiers. And in the second one, we focus on the channel distillation problems and trying to look at the fundamental limitations that are imposed on such a distillation process, in particular looking at the error that should happen in a distillation process. And in the third reference, we also look at the resource dilution cost and trying to look at the fundamental relations that hold between the distillable resource and the resource dilution cost, again, at the level of general resource theories. But before going to the details of these works, to introduce some resource theory framework to you guys, let me just have some brief introduction there. So it is always insightful to look at the theory of entanglement to talk about resource theory, because resource theory is pretty much a generalization of the idea for the theory of quantum entanglement. So the quantum entanglement, as we know, is a very essential quantum resource that underlines many quantum information processing. Then one of the ways of looking at this quantum entanglement is the operational one, where you imagine that Alice and Bob, two parties, are physically separated apart, then they can only make some local quantum operations and classical communications. So this is something known as LOCC. So if they are restricted to LOCC, then they cannot create entanglement from scratch. So instead, they have free access to some set of states known as a separable states. So this is not entangled states. So then the property of the LOCC is that from the separable state, you cannot create any entanglement from it. Then so you can now ask the operational question, can we transform some arbitrary state rho to some state sigma only using the LOCC operations? So these two are some freely accessible resources in your situations. So to answer this question, it turns out that it is insightful to look at some quantification of the quantum entanglement by using the entanglement measure, because the quantum entanglement is not a 0-1 concept, but if you're maybe some state is very close to the maximally entangled state, or that can be close to very separable, close to separable states. So these two states should have a different level of entanglement. Then this difference should be captured by this entanglement measure. Then turns out that if you look at this property, then you can also get insights into the feasible transformations under LOCC operations. Then, as I briefly mentioned, so this quantum entanglement can be characterized by these free states, separable states, and free operations being the LOCC, for instance. Then to measure the amount of entanglement, you can, for instance, take the relative entropy of entanglement measure, where the idea is that for given some state rho, you look at the closest separable state sigma with respect to the relative entropy measure. So this kind of gives you the idea of like how far your given state rho is from the set of your free states, separable states. But now interesting thing is that the quantum entanglement is not the only important quantum resource that underlies the quantum information processing. But for instance, if you're interested in the quantum superposition, then you're also motivated to kind of look at it quantitatively. So to address this question, we can now extend the idea of this operational theory of entanglement to the one where we can talk about this quantum superposition. By replacing this set of free states with some set of incoherent states, which do not have any superposition with respect to some preferred given basis, then in such a situation, you can, for instance, consider the free operations as the one that does not create any superposition from this incoherent states. Then, so how do we quantify the amount of superpositions? Then we can now borrow the idea from the entanglement theory and, for instance, look at this relative entropy measure as well. So look at the distance between your given state rho and the closest sigma that is in the set of incoherent states. So in this way, this kind of gives you the idea of how you take into account the important resource underlying in your situations. Then this idea can be generalized or like extended to much more number of quantum resources and leads to the idea of general resource theories. So we can just, write this picture, the same picture with the set of free states, free operations, and resource quantifier. Then this now gives you the general framework of dealing with the quantification and manipulation of some quantities that are considered precious under a given setting. So as we saw, this can be, of course, applied to quantum entanglement, but not only that, we can also apply that to, say, superposition or quantum thermodynamics or non-Gaussianity and so forth. So but it has been in a long time, this resource theory was developed in the individual fashion. Like once you set the set of free states and so forth, now you look at these individual settings, then trying to get some more understanding for such a situation, which is pretty important and insightful. But at the same time, we did not use much about this general picture. So because of this general framework, we are also motivated to have some general results that should be applied to a wide class of quantum resource that is encompassed in this framework, and in such a way that this extracts some features that are shared by wide class, many numbers of quantum resources. Then this is kind of nice because first of all, it gives you some handy result, because no matter what quantum resource that you kind of invent in the future, you can automatically apply such a results to those situations. But not only that, we can now get some fundamental connection between the different various kinds of quantum resources that may look quite different from each other on the surface. But if you inject this operational type perspective, then you can see now some tight relations between them. But we usually impose some wide assumptions that we consider the convex resource theories, where the set of free states are convex and closed sets. Then with this, the question is, what kind of results can we say that applies to this general picture? So now we can ask a little more, take a closer look. So what kind of question can we ask? So then one of the fundamental problems in the quantum information is the resource transformation, right? So the question is, if you're given some state rho and sigma, can we transform your state rho to state sigma only using some available operations? So in this case, free operations O. Then this problem itself is quite general, but you can also restrict attention to the more, some interesting, important operational tasks, which is a distillation and dilution as well. So, distillation process is basically, if you're given some noisy state rho, say like a noisy entangled state, for instance, then you try to manipulate them in a way that then transform it to some reference target state that how to use them, basically. So you transform this to the standard target class of target states. Then you look at how much target states you can distill from the noisy state. Our opposite task is known as resource dilution, where you start from the reference target state, and only using the free operations, you try to synthesize some noisy state rho. And then in a recent work, we characterize this the conditions for such a distillation and dilution to be possible at the level of general resource theories of the quantum states. So what I mean by general resource theory, again, is that we do not specify the set of free states, but this should be applicable to general situations. But we talked about these quantum state transformations. But now in this work, we take one step further than that, realizing that this quantum state is a special case of more general concepts of quantum channels. So as Mark Woody pointed out in his recent tweets, that the quantum, everything is basically quantum channel, which includes some quantum state, which is state preparation channel. Then a quantum measurement, a unitary evolution, or discarding system, or quantum channel, everything is basically quantum channel. So if you get some, if you are interested in some like general results, then having the results that can be applied to general quantum channels are strictly more, better or more general than having the results for the state transformation case. So this is one of the motivations that we want to consider channel transformations. And indeed, there also exist some situations that we do want to directly deal with these quantum channels as a direct resource to deal with. And this perspective also gives us an interesting idea where if you think about quantum channels, then this can also take into account several situations that involve the dynamical quantum resources, which of course can be characterized by quantum channels, but with some specific structures, such as nonlocality, contextuality, or measurement incompatibilities. So these have a specific channel structures, which takes in, for instance, classical variable to classical variable and so forth. But the recent resource theoretic approach for the channel transformation did not successfully take into account these cases. So this is one of the also another motivation that we try to introduce some general framework of the channel manipulation. Yeah, so when I talk about this channel manipulation, these quantum channels can be manipulated by something called the super channels. So the super channel was discussed in this reference back then. So this is basically, if you're given some channel E, then apply some this COM structure, which by the way can be also described as the combination of quantum channels. Then if you look at this one as an effective channel, then you can consider this as a transformation from channel E to channel N. Then with this, we can now introduce our resource theoretic framework pretty much the same way, where we replace the set of free states with the set of free channels, O. Then we can now consider some set of free super channels as a free operations that manipulate channels to channels. So in particular, if I write this S, then I collect every free super channel that does not create any resource for channel from a free super channel. So this is my notation. And we can now also consider some resource quantifiers that is a function from quantum channels to real numbers in the same motivation that you try to quantify the entanglement, but now this can be also defined for the quantum channels. So for instance, in the entanglement case, these free channels may be, again, the local operations classical communication, and some like a C-not gate that can create entanglement will be well outside of this set of free channels. Yeah, so with this, we can now introduce our framework of the channel transformations. So we can now consider this set of some channels of interest, which may have some specific structure that you are interested in, for instance, like non-circulating boxes. Then you consider some set of super channels that map this set of channels of interest to another set of channels of interest, which might have a different structure. Then as a free super channel, you consider the subset of this set of channels of interest. And your free super channel is something that maps your initial set of free channels to another set of free channels in the output space. Then with this, we can now lay down our question of resource transformation. So given channel E and channel N, does there exist a free super channel that maps channel E to channel N within the error epsilon? So this is our question. And in our work, we connect this conditions for transformability using the resource quantifiers that can be defined for the general resource theory of quantum channels. So let me now introduce some resource quantifiers that play major roles in this work. The first one is something called robustness measure. So this was first introduced in the quantification of entanglement first, then it was extended to other quantum resources as well. Then we talk about this in the level of quantum channels. So the idea of robustness measure is basically that that quantifies the amount of how robust your given channel is against a mixture with another channel. So if you're given some channel E, then you are to mix some another channel M so that this classical mixture of them becomes a free channel. Then this M is also inside a set of free channels for this case. Then you take a minimization for such a mixture level. And you also take a minimization over this channels M within this set of free channels. Then you can also consider some smooth version of it, where I take the minimization over some channels close to the given input channel E within this error epsilon, where this F is a channel fidelity, which is based on the state fidelity, but you take a minimization over it. So we can also consider another type of the robustness measure known as the generalized robustness measure. So they are almost the same, except this M can be outside of the set of free channels. So this can be outside here, like this. Then again, we take the minimum mixture level so that this classical mixture is going to be a free channel. Then the reason why I also write this max is that this is connected to the resource measure that can be defined based on the max relative entropy. So if you take a log of it, then this coincides with something known as max relative entropy measure. Then this is known as in the family of Renyi divergences. Then you can draw this kind of schematic where this is like a relative entropy measure. Then this is the max relative entropy measure. Then also this definition can tell you that this generalized robustness is smaller than or equal to the standard robustness by definition. So this inequality also holds like this standard robustness measure should be also upper bound of this max relative entropy measure. Then you could also look at the other edge of this Renyi family, which is known as mean relative entropy measure that is related to the hypothesis testing operational task. So this is precisely the second measure that we are going to look at that plays major roles in our work. So the hypothesis testing is pretty fundamental problems in the quantum information. Then you can consider this kind of divergence. And if you take a log of it, then that goes to the familiar hypothesis testing relative entropy measure. Then you can convert this to the channel measure by taking the optimization over the input state psi. But even you can also convert this to the resource measure by taking the minimization over the set of free channels. So this idea is basically the same as relative entropy measure, where you try to look at the smallest free channel from the given channel E. But depending on how to take the minimization, you can also consider another type of measure we call the affine hypothesis testing measure. So instead of taking minimization over O, I take the minimization over affine half of the free channels. So the reason we do that is basically that sometimes, depending on the situation you're talking about, if you try to connect this measure to the operational problem in a later part, then sometimes one of them becomes kind of trivial. But to get the meaningful results, we are to introduce this hypothesis testing measure. Then it turns out that this difference comes from the geometry of the set of free channels. Then as a special case of that, we can consider the mean relative entropy measure by taking the epsilon is 0 here. Then we can do the same thing to convert this to channel measures like this by taking optimization here, and also convert it to the resource measure like this. So with this, we are in a position to state our main results about the conditions for such a free transformation from channel E to channel N using the free super channels S within the error epsilon. So we phrase this in the necessary condition and sufficient condition form. So the necessary condition says that if there exists such a transformation, then this should always hold. Where this R is the arbitrary resource monotone, where this RE is the smoothing of such an arbitrary monotone. Then this basically tells you the monotonicity property for between epsilon and E and N, but this also takes into account the non-trivial factor that comes from this finite error that happens in this process in the form of this smoothing parameters. On the other hand, to talk about the sufficient conditions here, now we can find that this hypothesis testing relative entropy measure and robustness measure plays major roles. And in particular, if you compare this mean relative entropy or hypothesis type relative entropy, this and the robustness type measure. So this is standard robustness and generalized robustness. Then either of them holds. Then there exists such a transformation from E to N only using the free super channels. So this is a general relation that we saw. But if we kind of restrict our attention to a special case, then we can say a bit more than that. So if we focus on some resource distillation problems, what I mean by that is, so we transform some given channel E, noisy channel E, to some pure target channels. So a pure mean that if you input some pure state psi, then it output some pure state phi. So this is what I mean by a pure target channel. So this, for instance, includes a situation where if you talk about the state transformation case, then this corresponds to pure state preparations. And or if you talk about this dynamical resource transformations, then that can be a unitary gate. Then with this, on the top of the general results that I showed, we can also now connect this to the hypothesis testing relative entropy measure, smooth E. So this is a necessary condition. So you compare this hypothesis testing smoothing and mean relative entropy measure. And for the sufficient condition, we can now compare the hypothesis testing one and also generalized robustness type measure here. So using these general results, we can now get some exact characterizations of one-shot dilution and distillation cost at the level of general resource theory of quantum channels. To talk about that, we need to introduce some family of reference channels. So this is like the target resources that you consider in these situations. For instance, in the entanglement case, that can be a set of the Bell states, the level of Bell states with the different sizes. And in the dilution, resource dilution problem, you start from some one of the target channels and tries to manipulate it to your desired channel E. Then you look at the minimum level of your resource measure that is contained in the target channel T. And on the other hand, the distillation problem is that for given some channel E, you try to extract as much resource as possible only using the free super channels within this error epsilon. Then we can now get these kind of characterizations for such a one-shot dilution cost and one-shot distillation rate using the robustness type measure here, the standard robustness, generalized robustness, and hypothesis testing type resource measures under these conditions. So these conditions are kind of interesting. So this is saying that the relation between the different types of the resource measures, this is standard robustness and mean relative entropy measures, are evaluated for the target channels. So this is satisfied in many situations, including the entanglement transformations. But if you try to kind of phrase our result in a general sense, then we need kind of relations. Then we actually come back to this point later part of the talk. So this result has two meanings. The first one is that we can now get the general characterization of resource exchange in terms of this resource dilution and resource distillation problems. But now in the resource theoretical perspective, it also gives you some operational interpretation of resource measures of the generalized robustness measure, the hypothesis testing measures in terms of these resource transformations. So these were general results. So that's why we can apply our results to some specific settings that we are interested in. So as an example, let me look at the situation that kind of exploits the fact that we can deal with this quantum channels directly. So one of the major situations relevant here is the quantum communication. Because in the quantum communication, there is no underlying state theory that can just reduce your theory to. So these research theory channels are quite nicely fitted to this quantum communication setting. And in particular, there are two important figures of merits of the quantum communication. The one is the capacity, and one is the simulation cost. So the capacity is the idea that if you're given some noisy channel, then how much information can you send? Or you only using these noisy channels, and also encoding operations and decoding operations available. And a simulation cost is an opposite task, where if you try to realize some given channel E, and how much size of the identity channel is needed to synthesize your given channel E. But now we can see this as a resource distillation and dilution problems in our framework, because the one-shot capacity is pretty much you apply some free super channels that are available to you and try to get some identity channels. And the simulation cost is opposite things. So then we can now directly apply our results to this setting, then get some exact characterizations or such figures of merit in the several communication settings, such as separability-preserving codes or non-signaling assisted codes. And that gives some new insights and also recover some previously known results, but in a simple, single unified framework on the same footing. Then this also gives you some operational interpretation for applying hypothesis testing measure here as well. And we can also talk about the situation that might involve some specific structures, such as nonlocalities. So by appropriately setting some set of channels of interest and also a set of free channels, like a local hidden variable boxes. And now there have been several measures of nonlocality proposed before, but these can be understood in our framework as well, like a robustness measures and so forth. Then we can now give some operational applications for such a resource measures in this case, in terms of the box transmissions. Then we can, for instance, look at these isotropic boxes. So we can actually compute these resource measures like this. Then now by looking at one of the measures, like mean relative entropy measures, if you given some noisy box in this form, which is a convex mixture of the pure box and some free box, then you can conclude that no matter how many noisy boxes you have, only using the free super channels or free transformations, you can never get to your perfect pure box with with zero errors. So this itself was known before, but we can now reconstruct this in our framework as well. Yeah, so so now we talked about the conditions, characterization of the conditions for such a transformation to be possible. But in the second reference here, we give some slightly different perspective to the distillation problems. So to address the performance of such a distillation process, another way of looking at it is to look at the maximum distillation fidelity that is realized by this distillation process. So to do that, it's reasonable to look at this maximum distillation fidelity from this E to T using the free super channels. Then now the question is, can we characterize this maximal distillation fidelity using the some fundamental resource measures? So to do that, it turns out that it is helpful to bring up another resource measure known as weight measure. So this was again introduced for quantification of the entanglement theory, but now again extended to various situations. Then it can be defined quite general level. So this weight measure looks similar to the robustness measure in the sense that you also consider some classical mixture between the two channels. But it's slightly different because if you're given channel E, then you mix this M and N so that you realize this channel E. So this basically quantifies how much a free component is contained in this channel E. because this M is the free channel here. So then you take a max of it. So what is the maximum free component that is contained in this E? So this is an intuitive understanding of it. Whereas the robustness measure is a bit different because now a given channel E is here. Then indeed, these two resource measures behave differently, even qualitatively. Then this leads to two different bounds in our main results. So in here, we can now get the fundamental limitations on the distillation process in terms of the lower bound of the distillation error that should happen in your distillation process. Then we phrase that in terms of the resource measure using the weight measure and also a generalized robustness measure like here. Then this FOT is another resource measure that applied to this target channel T. So this is the fidelity-based resource measures. Basically, again, look at the closest free channel from the target channel T with respect to the channel fidelity. So we can now make comments on these main results. First of all, these two bounds give qualitatively different limitations. And in particular, for the first bound gives the no-go results, where if your channel E's Choi matrix has a full rank, then you cannot distill to some unitary gate at the zero error. So like there's no perfect distillation process allowed in such situations. And we can also use a second bound depending on situations. For instance, if this E is close to unitary, then this second bound gives you the better bound. So like you can really combine these two to get some fundamental limitations. And also you can consider arbitrary subset of the free superchannels. And since this applies to any free super channels. So this always gives you the lower bound of the error, no matter what your smaller set of free super channels you choose. So this was one-shot channel distillation in the characterizations. So what about the multi-copy? So what if you are given some multi-copies of the noisy channels E and trying to synthesize a purer target channel, which might have the few number of copies? So then this epsilon is again the free super channel in the sense that if these input channels are the free channels, then this also should map to some free channel. Then if you are talking about this channel manipulation, then unlike the state manipulations, we have different kinds of manipulations possible. So starting from this parallel manipulation, which might be the most intuitive one, but you could also consider some sequential manipulation or even adaptive quantum code that has some quantum memory involved in it, or even some quantum process without a definite causal order. So the question is, can we get some bound that are applied to any such kind of channel transformations? So this is our results. So like actually, this can be obtained from our main results in a kind of straightforward manner. So for any distillation protocol that includes every such situations, then we can now get the lower bound for a number of copies needed to assure this accuracy E, so this error E to a target channel T. So so then since we use the previous main results to get this, we can also get the two kinds of lower bound for the necessary number of copies with respect to the weight measure and also generalized robustness measure here. Then again, these bounds behave differently and have strengths in it. The first bound is useful for a small epsilon. So if target accuracy is very demanding, then it gives a very nice bound, then this gives you this fundamental scaling. And on the other hand, the second bound can give interesting implications for the asymptotic transformation and gives the strong converse bounds as we will come back later. But let me first apply our general results to one of the distillation process that people have been interested in quite recently. This is the magic state distillation protocol. So basically, magic state is something that that is useful for the fault-tolerant quantum computation then the problem is that you want to distill some pure magic state, given some noisy magic states, or even noisy magic gates, like a noisy T gate, then how to synthesize the better T gate or a CCZ gate, which is also a magicful gate. Then, the long research tries to find some good, protocol that, had some performance, but the fundamental limitations that should be imposed on arbitrary type of the distillation process was quite unclear. So our work can give some insights into it as follows. So this is an example of from noisy T gate to the CCZ gate. Then you can get some lower bound for the error that should happen in this distillation process. Then you can also see this as a state transformation case as well, like this. Then this yellow dotted line was the previously best known bound that should also apply to the general resource theories, but we get the state of art bound surpassing this previous known results. Then if you look at the number of copies necessary for realizing some error level E, then now the weight bound give a very nice the lower bound for such a number of copies, and also for the state case as well. So on the other hand, we can also talk about the asymptotic case starting from the one-shot bound. So this is related to the strong Converse bounds. So to remind you of some rate at the asymptotic situations, if I say the distillation rate, so this is, so you consider basically the situation where you are given some infinite number of copies of channel E, and then you try to manipulate it to the infinite number of copies of target channel T, and you basically look at the rate of these copies. Excuse me. And the distillation rate is the maximum rate at which this error vanishes at the n infinity limit. So this is the formula. So basically this epsilon is again the free process that I just I introduced. Then this should go to 1. So this fidelity go to 1, meaning that the error should go to 0 at the limit of n infinity. So you take a maximum such a rate that is possible. On the other hand, the strong Converse rate is the maximum rate at which error does not approach 1. So this means that if you're above this strong Converse rate, then your error rate is necessarily going to 1. So this is becomes pretty useless. So then by definition, this strong Converse rate is the upper bound of the usual distillation rate. Then if you can get the upper bound of the strong Converse rate, then we say that this is a strong Converse bound. Then it turns out that if we use our result, then we can get this strong Converse bound with respect to this max relative entropy measure, generalized robustness measure, and also this one. So this actually reconstructs some best known results for the strong Converse bounds for the quantum communication scenarios as a special case of our results. And we reconstructed in a more simple kind of unified framework as well in a one stroke. And I forgot to mention that if we focus also on the parallel manipulation rather than this general version, then we can tighten our bound. And this might be a little tighter than this Dmax bound. Yeah, so we were now talking about distillation protocols and look at the performance. But now in this third work, we now bring up this resource dilution again, and even ask a little different question, which is on the relation between the resource distillation and dilution cost. So what is the relation between them, basically? So this question was again studied quite intensely in the entanglement theory, especially the entangled state manipulations problems. Then distillable entanglement under LOCC can be defined in this way. This is the maximum rate that you can go from state rho to some Bell state. Then you make a copy of it. Then the entanglement cost on the other hand, starting from the Bell state and try to synthesize some copies of the noisy state rho. Then you can see this asymptotic yield cost relation. So yield is a resource yield and the cost is a resource cost. And this level entanglement is upper bounded by the entanglement cost. So which makes sense operationally, because if it was not, then one would be able to create the entanglement for free indefinitely, only using the LOCC. So this kind of breaks the second law, kind of things. However, if you're now looking at this non-asymptotic regime, which is a one-shot regime, which might involve some non-zero errors, then this relation gets a little subtle. But this problem was quite recently studied by Mark Wilde, where he looked at this one-shot entanglement yield like this, and one-shot entanglement cost like this. Then we can now he got this kind of one-shot relation that upper bounds this one-shot distillation entanglement with the cost, also involving some error parameters here. So for arbitrary error epsilon 1 and epsilon 2, then you get this relation where this epsilon prime is some function of epsilon 1 and epsilon 2. So now we've been interested in general perspective in the resource manipulations. We are naturally motivated to look at how general it can be. So is this yield cost relation unique to entanglement? So how far can we push this kind of relation to the general resource theory, or maybe quantum channel transformations? So this is what we are trying to do precisely. And to introduce this resource yield and cost in the general resource theory footing, we again look at some target channel T. Then the one-shot resource, this distributable resource, is now the maximum amount of resource that you can get from the noisy channel E, again, only using the free super channels here within this area epsilon. And you can now define the resource cost in the analogous way. Then we can get this, general results, which have this kind of one-shot, relation property, where we have some specific forms for this function form. And under this condition again, so like this condition, this kind of condition that keeps popping up, and we will come back to this point a little bit later. But this condition is also satisfied in many situations as well, actually. Then now again, we are interested in a specific case. Like one interesting thing is that if you get the one-shot bound, then we can go back and forth the symptotic bound and so forth. And so to see if this can be smoothly connected to the asymptotic understanding of the manipulations. So how is this related to asymptotic transformations? Then it turns out that not only can we get the asymptotic yield cost relation, but we can also get a strong converse inequalities. So to recap, this is the best rate at which error vanishes at the infinite copy limit. And this tilde version is the best rate at which error does not approach 1. So this is a strong converse rate. Then we can now get these strong converse inequalities where both either of the side can be now made a strong converse rate. So note that since by definition, this D tilde is greater than this D and C tilde is smaller than this C. So this gives you, the tighter bound than the one that does not have this tilde. So, however, now if you also restrict your, attention to the quantum state transformation problems, then now it turns out that we can make these inequalities to two-sided strong converse bounds. So again, under some additional condition here. So this can be applied. Hi.
Is 10 more minutes?
10 more minutes, yes. Okay, thank you.
Thank you.
Great. So this can be applied to the entanglement case. Then it solves one of the problems that posed in the recent paper by Mark Wilde. Yes, so now in these results, we kept saying like this kind of relations, like mean measure is a max measure, or mean measure is the generalized robustness, standard robustness measure, and so forth. So this gives you the idea that the resource evaluation, evaluating the resources for target channels or target states are quite important to characterize this manipulation problems at the level of general resource theories. So we are now interested in how can we understand this relation, and when does it happen, or can we connect this relation to some another problem, even possibly operational problems. Yeah, so this was kind of inspired by, again, old work from entanglement theory, where this LOCC twirling, which is an operation, free operation, can give you some insights into the resource evaluations. So this LOCC twirling operation maps states to the isotropic states, then fixes some state, Bell states, and also some complement states. So these isotropic states are the convex mixture between these two states. So using this operational perspective, one can get some simplified formula for some resource evaluations. So this is really then that now the question is that can we kind of introduce such a twirling-like operations in general resource theories, and how is that connected to our resource evaluations of some target resource? So we now focus on the quantum state transformations because this is the result what we get. So that we can now show that this phi is the target state you can consider. Then this inequality can be now connected to the existence of such a free operation in this form. This has some property that's alike the LOCC twirling, in the sense that this fixes the reference state phi and also a complement state sigma star. The sigma star is the orthogonal state from the reference state phi. Then you can get more results from that, but this allows for the exact resource evaluation for isotropic-like states, including the smooth version of the resource measures, such as the hypothesis testing and so forth, that a priori involves some complicated optimization problems there. Then we can also apply this technique to evaluating some resource states in the resource theory magic states. Then we can get some exact evaluations for some resource magicness evaluations. So we discussed that in our manuscript. Yeah, so let me summarize this whole talk. So I kind of present some results that share the interest in the characterizing the manipulation of general dynamical quantum resources. In the first one, we introduced a general framework of the one-shot resource manipulation that are applicable to a broad class of dynamical resource theories, which might have even specific structures. And we characterize such a one-shot resource transformability in terms of the resource quantifiers that are based on the entropic divergences and that can be defined at the level of general resource theories. Then we apply such a finding to specific examples in which this dynamical resource treatment is quite useful, including the quantum communications and the nonlocality. Then provided operational applications to these resource measures. And in the second work, we look at the distillation process in a little different way and put the fundamental lower bounds on the distillation errors. And we apply that to the magic state distillation problems. And finally, we look at now the relations between the resource yield and the resource cost, and derived some inequality that applies to general resource theories. And finally, we also connected the resource evaluations to some twirling-like operations inspired from the entanglement theory. So in the future work, it would be interesting to have in-depth study on the resource transformations for situations that might have some specific structures. And also, it would be interesting to have a further characterization of the relations between the different kind of resource measures. We slightly did that partially, but we are still trying to understand when exactly this situation happens. And also, finally, looking at the asymptotic behavior of some channel resource measures are quite interesting. So if we get the one-shot bound, then if you try to take it to the asymptotic limit, then this kind of involves the evaluation of the multi-copies resource measures. So this is also an interesting open problem. So with this, I thank you for your attention.
So thank you. Can you hear us?
Yes, I can hear you.
Great. Thanks for a nice talk. and a lot of nice results on the theory of resources. I'm pretty sure there might be some questions. So look, if you have any question, maybe the best idea is to come here and ask a question. Are there any? So, come in. Maybe you
yes. Hey,
maybe it's best to show up.
Hey, hello. So I would have one technical question, maybe from the beginning. You said something about this affine combinations. When you were looking for a resource measure, you didn't look for the resource measure with respect to free states, but like these affine combinations. Like, what's kind of physical intuition behind this? Why can you use it, and why it's useful?
Yeah, so in particular, this affine combination thing appears when your set of, suppose you have a state theory for simplistic, then you have a set of free states that does not have full measure. So like if you have some like sort of squashed, sheet of the free states, such as coherent theory and so forth, then, for instance, the standard robustness measure diverges this kind of situations because you cannot span your whole state systems. So in such a case, this affine measure still gives you some result. Basically, affine measure you take so basically, affine measure you look at this affine space, right? So this is friendly to such a situation.
So and it's a technical trick basically to be able to apply this theory to a bigger set of resource theories, right?
Yes.
In a sense.
Then, for instance, like if you talk about quantum communication now, then we discussed this non-signaling assisted codes. Then corresponding free channels is the constant channel, set of constant channels, basically put anything into some fixed state. So this is reduced dimensional in the sense that your free channel is squashed. So then this gives you the meaningful results. So like affine hypothesis testing in this way comes up and gives you the characterization.
Okay, thanks. I have some more questions, but maybe somebody else has some questions.
Well, so let me ask maybe now one. Can you hear me?
Yeah.
So in the very first slides, you introduce the theory of resources, and then you use those idea like measure of quantities. Let's take here, like entanglement measure. So usually we assume it's kind of a distance of this object from this set of free states. This is a very simple approach. But then if you consider this relative entropy of entanglement, for instance, it's not really a distance, it's not symmetric. So the question is simple. Does it play any role if you really use a distance for this purpose, or it could be any more generalized quantity like quasi-distance?
Yeah, good question. So I would say that the most fundamental property that we use is more like a contractivity of such a function. So if you apply some free operation and we want it to decrease or not increase. So for instance, relative entropy satisfies such a relation, and that's why it works. So so if you are interested in, I guess, more specific operational property, then for instance, looking at the trace distance give you directly some understanding of the distinguishabilities. But I think to formalize the resource measures, for that to be proper distance measure does not really matter. But depending on the operational problem that you're interested in, it gives you the different answer, I think, for that.
Okay, thank you very much. Are there any further questions by